Let's look at an example of a paired difference t-test and confidence interval. The Chinese herb kudzu has long been thought to reduce alcohol intake. It's been used in Chinese medicine for hundreds of years to treat the effects of alcohol. Scientific experiments have shown that it reduces alcohol consumption in rats. In an experiment, researchers investigated the effect of puerarin, an extract of kudzu, on alcohol intake in humans. 10 heavy drinkers were recruited for the study. On 2 separate occasions, the individuals were allowed to drink up to 6 beers over a 1.5-hour period while watching TV or reading. This was done in an apartment-like setting. They were supplied with beer, and their beer consumption was carefully monitored by weighing it on a scale. For 1 week prior to each drinking session, the participants took either a dose of puerarin each day or a placebo each day. Each individual took the puerarin for 1 week and had a drinking session, and the placebo for 1 week and had a drinking session. The order in which they did this was randomized. This was a double-blind study, so the individual did not know whether they were receiving the puerarin or a placebo. We are interested in estimating what effect, if any, puerarin has on alcohol intake. Here are the results, the total weight of beer consumed. First, note that we have 2 observations on each individual. On individual 1, we had measurements for the placebo and the puerarin, as we have for individual 2 and individual 3 and all the way down. So here we have dependent samples, and methods based on independent samples would not be appropriate here. We're going to use the paired difference procedure to analyze this data. To do so, we first take the differences within each pair. So on this first individual, I'm going to take the measurement for puerarin and subtract that of the placebo, and I would get minus 1,235 grams. I just as easily could have gone placebo minus puerarin. It doesn't really matter as long as we keep track so we can reach the appropriate conclusions in the end. This second individual, 1635 minus 1919, would be minus 284 grams. And we do the same thing all the way along. If we were to do this for every individual, we'd end up with these 10 differences. And now these 10 differences represent our single sample, and we're going to use one sample t procedures to analyze these differences. If we took the mean of the differences, we would see that x bar is equal to minus 386.1 grams. That is very roughly 1 beer. So in this experiment, on average, people taking the puerarin drank 1 beer less than when they took the placebo. We could also calculate the standard deviation of those differences, and we would find that S, our sample standard deviation of those differences, is 635.4 grams. In this experiment at least, when on puerarin, people drank less alcohol on average. But is this a significant difference? We're going to investigate that in a minute, but first let's look at a box plot of these differences. Here's a box plot of the differences, and we can see that the values tend to be negative, indicating that people on puerarin tended to drink less alcohol. Now I'm going to put in a red dot representing the sample mean and a line at 0. Here's the sample mean down here at minus 386, and this line is drawn in at 0, which is the value we would expect to get on average if puerarin had the same effect as a placebo. And we see this difference here between our observed sample mean and this value at 0. And we want to know if that is a significant difference. And we're going to investigate that by carrying out a one-sample t-test, and we'll also construct a confidence interval. But we only have 10 observations, and so the use of the t procedures is a little bit sketchy, and it's heavily reliant on the normality assumption. So let's investigate the normality assumption by plotting a normal quantile-quantile plot. Recall that in a normal quantile-quantile plot, the points lie in an approximately straight line if the data is approximately normally distributed. Here there are a few points that are a little extreme, and so we may not feel all that comfortable using the t procedures, especially for such a small sample size. And it's a little iffy here, but I'm going to go ahead and use them to illustrate the procedures. First, let's construct a 95% confidence interval for the population mean difference. Here I give the summary statistics again, along with the appropriate confidence interval formula. And the standard error of x bar is our usual standard error of our sample mean in one-sample problems, which is simply s, our sample standard deviation, divided by the square root of n. We're almost ready to calculate the interval, but we need to find this t-value first. But we need the degrees of freedom to do that, and the degrees of freedom for our one-sample problems are n minus 1, and here that's going to be 10 minus 1, or 9. And so we can go to software, or the t-table, and we could find that for those degrees of freedom, t.025 is 2.262. So now we can calculate our interval. Our interval is going to be minus 386.1 grams plus and minus 2.262 times the standard error, which is made up of the sample standard deviation of 635.4 over the square root of n, which is 10. And this works out to minus 386.1 plus and minus 454.5. And if we carry out the addition and subtraction, we'd see that that's minus 841 to 68. I'm doing a little rounding here, although you should carry many decimal places throughout your calculations. We can be 95% confident that mu, the population mean difference, lies somewhere within this interval. But what does that mean in the context of this problem? We can be 95% confident that mu, the true mean difference in alcohol consumption, lies somewhere between minus 841 grams and 68 grams. And so, according to this confidence interval, the true mean reduction in alcohol intake when taking puerarin could be as much as 841 grams, but it could also result in less of a decrease than that, or even up to an increase of 68 grams on average. Note that 0 is within this interval. So, according to this interval, 0 is a plausible value of the population mean difference. And so, based on the interval, there isn't strong evidence of an effect of this puerarin. But let's look at that more formally with a hypothesis test. Let's test the null hypothesis that puerarin has no effect on alcohol consumption, which symbolically is that mu, the population mean difference, is 0. And suppose we feel that a significance level of 0.05 is appropriate for this particular problem. The null hypothesis is that puerarin has no effect. But what is an appropriate alternative hypothesis? Well, as is often the case, that's debatable. But we do have a body of evidence from past research that tells us kudzu may reduce alcohol consumption. So it would be reasonable to choose this one-sided alternative hypothesis that mu is less than 0. One could also argue for a two-sided alternative hypothesis here, but a one-sided alternative is reasonable given the setting, and it's what the researchers chose in the original paper, so I'm going to go with it. Here we have the summary statistics and the appropriate t-test statistic. And recall again that our standard error of x bar is simply the standard deviation divided by the square root of n. And so our test statistic is our sample mean of minus 386.1 minus the hypothesized value of 0 divided by the standard deviation of 635.4 over the square root of 10. And this works out to minus 1.922. Now we need to find the p-value. And the degrees of freedom again are n minus 1, or 10 minus 1, which is 9. So let's see what our test statistic looks like on a t-distribution with 9 degrees of freedom. Here's a t-distribution with 9 degrees of freedom. And our observed value of our test statistic was minus 1.922, which is somewhere around there. It's out in the left tail. It's a little far out, but not that far out. What is the p-value? Well, for this alternative hypothesis, mu less than 0, The p-value is the probability under the null hypothesis of getting the value we got or something even farther to the left, or in other words, the area to the left of that value under this t-distribution. If we use software, we can find that the p-value is, to 3 decimal places, 0.043. The p-value is fairly small and less than this given significance level of 0.05. And this means we have significant evidence against the null hypothesis at the 5% significance level. There is significant evidence that the population mean is in fact less than 0. But what does that mean in the context of this problem? It means there is significant evidence at the 5% significance level that puerarin decreases beer consumption, with our one-sided p-value of 0.043. Since this was a well-designed and randomized experiment, this gives evidence that puerarin actually causes a reduction in alcohol consumption. The point estimate of the mean difference in consumption is approximately minus 386 grams, which was about 1 beer. Note that we found significant evidence against the null hypothesis at the 5% level, even though the 95% confidence interval for mu contained 0. The exact relationship between hypothesis tests and confidence intervals that we've discussed previously doesn't hold here, since the confidence interval was two-sided, but the hypothesis test was one-sided. People do sometimes choose a one-sided alternative hypothesis to cheat a little bit in an effort to find significance, but that goes against everything that we believe in statistics. If you want to use a one-sided alternative hypothesis, you should have a very compelling reason for doing so, one that you could justify before ever looking at your data.